Hi, I hope you are enjoying the ITCS conference, and thanks for coming to our talk. My name is Kevin Tian, and I'm excited to share with you our recent work titled Relative Lipschitzness in Extragradient Methods, and a direct recipe for acceleration. This is joint work with Michael B. Cohen from MIT and my advisor, Aaron Sidford from Stanford. In our paper, we study algorithms for a broad family of problems called solving variational inequalities, or VIs, in monotone operators. If I had to briefly summarize the main takeaways of our work, they would be as follows. First, we show that a more fine-grained analysis of existing algorithms for solving VIs, based on bounding a parameter we call relative Lipschitzness, yields improved rates of convergence in various interesting applications. Notably, a number of custom analyses for solving special cases of VIs, which yield rates not predicted by the standard VI theory, and appear somewhat disparate at a glance, fall under our framework and thus can be explained by a single unified technique. The resulting proofs are usually quite straightforward, and amount to a few applications of Cauchy-Schwarz, and we hope they demystified these previous analyses. So one example of such a special VI algorithm I'll focus on in this talk is Nesterov's accelerated gradient descent. This algorithm was introduced in the 80s and is a landmark result in optimization theory, but its proof has been described by experts as quite mysterious. In this talk, we will see a complete novel proof of acceleration as an instance of another existing optimization algorithm. This is the first such example to our knowledge. Our paper also defines the expected version of relative Lipschitzness and shows that a new analysis of stochastic VI algorithms yields improved rates for structured problems and more fine-grained randomized accelerated methods that are found in the literature. Finally, a third application captured by our framework is approximation algorithms for undirected mass flow. In particular, we show that the area convexity framework recently proposed by Sherman for this problem is recovered by a fine-grained analysis of standard VI algorithms. Our framework also extends to a number of other interesting settings, improving in some regimes fine-grained rates for minimax optimization, and recovering so-called optimistic analyses of mirror descent. Now, before we jump into the details, I wanted to give a brief overview of how to watch this talk. The main theme I try to capture is what I wish someone had told me about variational inequalities and acceleration before we started this project. In fact, this project basically fell out of trying to re-understand these algorithms from first principles, and this is the spirit I hope to try to convey in my talk. The first half of the talk will largely be a primer on extragradient methods for solving VIs, so don't worry if these words don't mean anything to you right now. I'll try to make the goals of the algorithm as intuitive as possible, and seeing the analysis will make it easier to appreciate the main definition of this paper, which is relative Lipschitzness. For the experts watching this talk, feel free to jump ahead if you don't need the primer. After stating the condition we use to analyze the convergence rate of extragradient methods, we'll immediately see the payoff. So as promised, I'll give a complete proof of acceleration, accepting one or two technical details. And the proof will fall out of our framework quite straightforwardly, and a couple of simple calculations. And finally, the last part of the talk will be about some further applications and generalizations of our method to local and randomized settings. I'll conclude with some thoughts on future directions to take our framework. To start, I'll begin by describing the problem family we study. A VI problem is parameterized by a monotone operator G from a set to its dual, which satisfies the displayed condition. Informally, it forces the results of the operator on 2 points to be aligned with the direction between these 2 points. We'll mostly only consider two examples of monotone operators in this talk. The first is just the gradient of a convex function, and we'll prove this is monotone in just a second. The second is what we call the gradient operator of a convex concave function on 2 blocks. And notice that the second block of G is negated. So when talking about a convex concave function, we'll always call the convex block X and the concave block Y. Now, to convince yourself that example 1 is really a monotone operator, the proof just sums convexity from X to Y and convexity from Y to X. And the proof that example 2 is monotone is very, very similar. We now define variational inequalities. In short, solving a VI in a monotone operator G just asks us to find a point X star such that the inner product between G of X star and X star minus X for any X in the domain is non-positive. For those familiar with mirror descent algorithms, this condition has a natural interpretation as a one-step regret guarantee. In the case of example 1, this amounts to just minimizing the convex function. The fact that this solves the associated VI in the gradient is commonly referred to as first-order optimality. In the case of example 2, the solution of the VI is a saddle point, or Nash equilibrium of the convex concave function. And the proof that solving the VI for a convex concave game yields a saddle point follows from the observation that the inner product of G and the difference between the point that's the argument for G and any other point x, y upper bounds the difference between f of x star y and f of x y star. And if you haven't seen this before, this proof just follows from an application of convexity and concavity. And it has a natural interpretation as the change in utility from two players x star, y star, deviating in their responses to new points, x and y. Maximizing this quantity over all choices x and y is commonly referred to as a duality gap. And when the duality gap is non-positive, we have found an equilibrium. And we'll basically only be discussing one family of algorithms for solving VIs in this talk. And we'll collectively refer to them as Extragradient methods. They were first analyzed in the context of Lipschitz operators by Nemirovsky and Nesterov 15 years ago. We'll be focusing on Nemirovsky's version in this talk, but we also discussed Nesterov's version in the paper. These methods apply to a VI in an operator G and are driven by regularizer R. And the pair G, R defines the steps of the algorithm. Typically, when analyzing extragradient methods, the regularizer R is assumed to be strongly convex, which means it has some positive curvature in a specified norm. This is a strengthening of the standard convexity definition, which allows for zero curvature. A typical example is when R is just a squared Euclidean distance. We'll later talk about how to relax this assumption of strong convexity of R. Now we'll talk about rates for extragradient methods with a strongly convex regularizer. In 2004, Nemirovsky showed that when the operator G is Lipschitz with parameter lambda, the method converges to a solution at a rate of lambda over t in t iterations. Under the assumption that the operator G is not only monotone, but also M strongly monotone with respect to the regularizer R, which is the definition here, the method converges at the displayed rate. So roughly you can think that the distance to the optimizer decreases by a constant factor every lambda over M iterations. If this is your first time seeing these kinds of rates, I encourage you to pause the video now to familiarize yourself with them. They'll serve as benchmarks for the rest of the talk. So we summarized the classical rates of extragradient methods on the left of this slide for reference, which is what we just discussed. Basically, assuming that the regularizer is strongly convex and the operator is Lipschitz, the method is converging at a lambda over t rate. And under the further assumption that the operator is strongly monotone, the rate is exponential in this parameter lambda over m. And you can think of this parameter as a condition number for monotone operators. Under these minimal assumptions, these rates were both shown to be tight, even in the case when the norm everything is measured in is Euclidean. However, for a number of structured examples of variational inequalities, it's known that we can improve upon the rates predicted by this standard theory. Perhaps the most famous example of a known improvement is the case of solving a VI in a gradient of a convex function. So as a reminder, this is equivalent to just minimizing the function. Nesterov's accelerated gradient descent method roughly obtains a quadratic improvement on the predictions of standard extragradient analyses for just this special case. Another more recent example of a structured case yielding improvements, which we think is of particular interest to a TCS audience, is that of L-infinity regression. And this setup has applications to Maxflow, which we'll elaborate on later. Obtaining 1 over t rates of convergence for this problem using standard techniques without worse dependence on dimensions was a notorious obstacle until a breakthrough work of Sherman in 2017. This obstacle was because known lower bounds showed that any strongly convex function in this norm has diameter growing linearly with the problem dimension, and was overcome by a new analysis called area convexity. Finally, a number of other mysteries surround extragradient methods. For example, it remains unclear what types of structured VIs allow for 1 over t rates of convergence via stochastic methods, which would match the rate of their deterministic counterparts in terms of dependence on t. And in another line of research, a perspective known as optimism was proposed to analyze these algorithms, which we'll talk about briefly later. So the main conceptual contribution of our paper is a new condition characterizing the convergence rate of extragradient methods beyond this standard setup of a Lipschitz G and a strongly convex R. And our new characterization boils down to a simple to verify relationship between the pair G and R. And we show that this new framework captures the tailored analyses of several of the structured instances that we mentioned. So we'll now give a gentle introduction to extragradient algorithms. And we'll start by describing an idealized version of these methods, which is known as the proximal point method. So for the next few slides, we're going to focus on the special case of minimizing a convex function f. Consider defining a sequence of iterates by the displayed equation. The function v v of r, v superscript r sub xk is known as the Bregman divergence from a point xk. And you can think of it as a possibly non-Euclidean notion of distance. And intuitively, the objective to finding the next iterate is a trust region method. It tries to minimize the function f, which is the overall goal, without straying too far from the previous iterate. By tuning the parameter lambda, we interpolate between these two goals. We now formally define the Bregman divergence. It's simply the difference between r of x and a linear approximation of it from a point xk. And when r is convex, the divergence is always non-negative. And when it's further strongly convex, the divergence grows at least quadratically with the distance. If this is your first time seeing this, it's useful to keep the example when r is just the Euclidean quadratic regularizer in mind. And in this case, the divergence is the Euclidean distance squared. We'll leave the, the definition of divergence here for convenience. And by directly writing down the first order optimality conditions of the minimization problem in defining xk plus 1, we arrive at the displayed equation. By a well-known manipulation, the right-hand inner product can be written as a relationship between three Bregman divergences. And we'll simply drop the third divergence because it's always non-negative. This leads us to the main technical claim for the proximal point method, which we summarize here. And by directly applying this claim in a few different ways, this leads to different convergence guarantees under a few different settings. By directly summing this guarantee over t iterations and taking an average, we see by convexity that the approximation error of the average iterate goes down at roughly a lambda over t rate. And the key observation here is that the right-hand side telescopes. So we simply pay the initial divergence averaged over all the iterations, the right-hand side being the difference of Bregman divergences. If you further assume that the gradient is one strongly monotone with respect to the regularizer, which basically means the function f itself is strongly convex, it's not hard to see that combining this with the first order optimality condition above means that the divergence to the minimizer, x star, is shrinking by roughly a 1 over lambda factor every iteration. So this means that up to a logarithmic term, we can find a highly accurate optimizer of the function in lambda iterations. And you might notice that so far I haven't said anything about what the parameter lambda actually is. And you can think of this lambda as a step size. The reason I haven't said anything is because the proximal point method is just an idealized algorithm. So typically it's not easy to actually compute in closed form the iterates that it defines. But intuitively, the smaller that lambda is, the faster the convergence rate of the method, but the more expensive the problems defining the iterates might be, because they look more and more like our original problem, which is just minimizing f. So I've summarized the key takeaways of the previous slides here. In short, the proximal point method is just an idealized method for minimizing a function f, which solves a sequence of subproblems, each of which minimizes f plus a regularizer. And the main technical lemma about the iterates is also written here, which we just proved. A classical first order method known as mere descent basically modifies the problems defining these iterates slightly. So instead of minimizing the regularized function, mere descent repeatedly minimizes regularized linearizations of the function. And when the regularizer R is simple, we can actually compute these linearized iterates in closed form. Compared to the optimality guarantees of proximal point, the optimality conditions of mere descent are very similar. And in fact, the only difference here is that the left-hand side has a gradient of xk, the previous iterate, rather than xk plus 1. This is because we minimize the linearization instead of the function itself. However, in order to convert this guarantee into function error, we'd really like the gradient of the next iterate, xk plus 1. So to remedy this, we just add the difference between the gradient inner products to both sides. So this extra term that pops up can basically be thought of as a discretization error. And ultimately controlling this error will lead to a trade-off on the step size lambda that we take. If we make lambda larger, again, we'll get a slower convergence rate, but the discretization error that we showed here will also become smaller, which is good. So finally, we have all the intuition we need to define extragradient methods. Here's the basic idea. We really want the optimality conditions of the next iterate, xk plus 1, to have its own gradient in the picture. So this corresponds to the proximal point method. So informally, you can think of this next iterate, xk plus 1, as the solution to a fixed point iteration, because its own gradient shows up in the optimality guarantee. And extragradient methods basically just take mere descent to the next level by iterating a few steps in order to hope to simulate this fixed point iteration. Here's what the extragradient method with exactly 2 iterations looks like. And it's the algorithm that we'll focus on for the rest of the talk. So this extragradient method with exactly 2 steps is called the mirror-prox method in the literature, and was analyzed by Nemirovsky in 2004. So his main observation was that when the operator G is Lipschitz, and the regularizer R is strongly convex, you only need 2 iterations of this extragradient method to recover the 1/2 rate of convergence for the ideal proximal point method. The proof strategy is quite straightforward. So similar to mirror descent, if you do an analysis of mirror prox, a discretization error term pops out of the first order optimality conditions. And the key takeaway of Nemirovsky's work is that the discretization error actually doesn't hurt us as long as we take a large enough value of the parameter lambda. So in particular, when the operator is L-Lipschitz, Nemirovsky showed that the discretization error is non-positive for all lambda at least L, so all large enough lambda. And the condition we propose in our work for analyzing extragradient methods just directly falls out of this analysis. So we just call this total requirement that the discretization error be non-positive a relative Lipschitzness condition. So we named this following a similar condition called relative smoothness, which appeared in the convex optimization literature, so just minimizing a convex function. And note that a condition can be concisely described as the relationship between the operator G and a regularizer R, localized to the points in any particular iteration. So when G and R satisfy this relationship with some parameter lambda, we say that G is lambda relative to Lipschitz with respect to R. Intuitively, the left-hand side of this guarantee can be thought of as how much the operator G dilates an inner product defined by 3 points. And the right-hand side just asks, what multiple of the divergences between these points do we need to upper bound these inner products? I should mention that this condition is quite natural, and its statement actually appeared in independent work earlier this year by Stanford et al. However, I want to emphasize that we view the observation that applying this condition to a number of important applications yields improved convergence rates as our key novel contribution of this work. So we'll first show that a straightforward adaptation of Nemirovsky's mirror prox analysis shows that when operator G is lambda relatively Lipschitz in R, we obtain a lambda over T rate of convergence. So this just follows straight out of the mirror prox proof we saw earlier. And when G further satisfies both relative Lipschitzness and strong monotonicity, the rate of convergence improves exponentially to linear in the ratio lambda over m. So note that both of these rates match the earlier standard BI setup rates that we showed earlier. We wanted to emphasize that our new condition is a looser requirement than the traditional analysis, which requires G to be Lipschitz and R to be strongly convex. And a few applications of basic inequalities show that an operator regularizer pair satisfying the standard more stringent requirements also satisfies relative Lipschitzness. And we'll demonstrate this now. So by applying Young's inequality, we can bound the inner product on the left-hand side of the RL definition as so. And by using that G is Lipschitz and the Bregman divergences of a strongly convex function are themselves strongly convex, we get the RL condition. However, we emphasize that in several important cases, even when the operator is not Lipschitz and the regularizer is not strongly convex, the pair still satisfies our definition and gets a better convergence rate for that reason. So we can now discuss our main application, the punchline, which is recovering accelerated rates for convex optimization. And we'll focus on the following setup. Let f be a convex function we are trying to minimize, and assume that its gradient is L-Lipschitz and the function itself is mu strongly convex. We'll assume that the relevant norm is Euclidean for now, but in the paper we deal with general norms. And it's well known that this setup is equivalent to upper and lower bounds on the eigenvalues of the second derivative matrix of f. A naive way of solving the associated variant vi, or in simpler terms, just minimizing f, is just letting g be the gradient of f. Then by using the framework of the previous slide, since g is L-Lipschitz and mu is strongly monotone, when using the squared Euclidean norm as the regularizer, the extragradient algorithm halves the error in roughly L over mu iterations. However, even in the 80s, Nesterov knew that we could obtain a faster convergence rate by accelerated gradient descent, depending instead on the square root of L over mu. And the key question here is, can we show that this is not actually a limitation of extragradient methods? It turns out the key insight is to slightly rewrite the problem into an equivalent minimax optimization problem. This minimax optimization formulation was called the Fenchel game by Wong and Abernathy in 2018. Let H be the result of subtracting mu over 2 times the squared Euclidean norm from F. And notice by the strong convexity assumption, the function H itself is still convex. The Fenchel game we define is in terms of the Fenchel dual of the function H. This function, which we call H star, is sometimes also called the convex conjugate. And the definition of H star, which is also displayed here for convenience, is just basically copy-pasted into the minimax formulation. We're essentially only going to use two facts about the convex conjugate. The first is that H star is 1 over L strongly convex, which is well known to follow from the fact that H is L smooth. The second is that the maximizing argument in the definition of H star can be written as a gradient of H. It's not hard to see that the saddle point of the Fenchel game has in its first block the minimizer of the original function f. To solve the Fenchel game problem, our choice of algorithm is just mere prox. And to define the algorithm, we also need to specify an operator g and regularizer r. The operator g is just going to be the gradient operator of the Fenchel game, which is convex concave. And we'll use a separable regularizer to drive the algorithm, which is the sum of mu over 2 times squared Euclidean norm on x block and h star, the Fenchel dual, on the y block. So following our framework, to obtain a rate of the algorithm, we just need to prove two bounds. The first is just that the operator g is exactly one strongly monotone with respect to the regularizer we defined. This follows since the operator is almost exactly the sign gradient of r, plus the result of a bilinear coupling term. In the definition of g, this coupling term ends up exactly canceling out. So all that's left is just to bound the RL parameter between the pair g and r. So just as a reminder, we can write the definition of RL here. And it involves 3 points, which we call z, w, and u. Note that each of these points actually has two blocks, which is superscript as x and y. So sorry for a lot of notation, but hopefully it's clear what I mean. And we went ahead and expanded out the left-hand side of the definition. It involves 4 inner products. We can think of the first two inner products as non-cross terms, since they only involve inner products between x variables and x variables, or y and y. It turns out that these two inner products are straightforward to upper bound in terms of Bregman divergences. Essentially, well-known inequalities, which just follow from convexity, show that the non-cross terms contribute one multiple of the right-hand side to the RL bound. So far we're at lambda equals 1. The bottleneck for the rate follows from the RL for the cross terms, and these are the terms involving an inner product between y variables and x variables. So to bound these, we start by applying Cauchy-Schwarz, and then by using Young's inequality, we obtain the following bounding products. However, each of the sums in the parentheses can now be bounded by a Bregman divergence in the regularizer R. So to see this, we use that the x bound, the x block of the regularizer is mu strongly convex, and the y block is 1 over L strongly convex. So overall, these terms contribute a square root L over mu multiple of the right-hand side to the RL bound. Note that in order to obtain these bound on the non-cross terms, we had to crucially use interactions between the primal and the dual blocks. So one interpretation of this is that acceleration is fundamentally a primal dual phenomenon. And finally, putting together both bounds shows that G is 1 plus square root L over mu, relatively Lipschitz with respect to R. There is a technical detail that we haven't described how to solve the subproblems defining the iterates. It's actually quite straightforward to implement these steps for the x block, but for the y block, we can use the fact that, that maximizing arguments for the Fenchel subproblem are actually gradients. And this lets us maintain the y variables implicitly throughout the algorithm, where we explicitly compute the points that they are gradient of and maintain those. The idea of regularizing the dual function with itself and the observation that the iterations are actually implementable are very crucial to our rate. And we think this is a nice trick and hope it has further applications. And putting together the strong monotonicity bound of the previous slide, the RL bound of this slide, and this implicit maintenance trick gives a complete accelerated algorithm. We'll give a short description of a few other interesting applications of RL and its extensions that we define in our paper. The first uses what we call local relative Lipschitzness, which is just a fancy way of saying the analysis of extragradient methods only actually cares about RL applied to the iterates of the algorithm rather than totally arbitrary points. We apply this tool to an application in computing approximate undirected maximum flows. It was observed by breakthrough works of Sherman, Kellner, et al., and Peng that the problem of approximate max flow can be reduced to a small number of combinatorially preconditioned L-infinity regression problems. The resulting regression matrix has a polylogarithmic L-infinity operator norm. As we briefly alluded to earlier, one difficulty in applying the standard extragradient analysis to this regression problem is the fact that that the standard analysis requires a strongly convex regularizer. And it turns out that there's no strongly convex regularizer in the L infinity norm of a box over a box, whose size scales sublinearly in the problem dimension. So this leads to worse rates. Sherman actually showed how to overcome this difficulty in a breakthrough work in 2017 by considering a primal dual form of L infinity regression. And he solved the associated VI by designing a new extragradient algorithm and analyzed it through a weakening of strong convexity, which he called area convexity. In our work, we showed that the original extragradient algorithms of Nemirovsky and Nesterov applied to this VI problem, when driven by Sherman's regularizer, also obtained the same rates of the constants. The proof follows directly from a RL bound. And crucially in the proof, we use the fact that the iterates on one of the blocks is stable up to constant factors, so we can obtain a stronger local bound. A second property of the RL framework is that it extends fairly straightforwardly to randomization. To provide some context, there's a general gap in our understanding of stochastic variance of extragradient methods. In particular, under a bounded variance assumption on the stochastic operators used, the resulting convergence rate of extragradient methods scales as t to the minus 1/2, which is worse than their deterministic counterparts. But on the other hand, for specific cases of VIs, such as stochastic convex optimization, it's actually known how to design reduced variance randomized operators, which obtain convergence rates scaling like 1/t. And the natural question is, can these variance reduced operators be extended more generally to extragradient methods? One difficulty behind using randomness in extragradient methods is that the randomness of the first gradient step already causes a variation in the second step. So even notions like unbiasedness become a bit hard to define, since the intermediate iterates themselves are also random. We give a simple set of conditions which randomized extragradient methods can converge, which allow them to converge at a 1/t rate, which makes progress towards understanding this mystery. This formalizes and generalizes ideas from earlier work of Aaron and me on coordinate methods for max flow. And basically the point is, if a notion of unbiasedness holds with respect to an average intermediate point, x bar, and an expected version of relative Lipschitzness hold, we recover similar stochastic rates as the deterministic counterparts, but with possibly much cheaper iterations. Because our randomized algorithms makes the gradient operators of intermediate iterates share randomness, we describe our method as a local variance reduction method. We showed that by applying this framework to the Fenchel game, we can recover rates of randomized accelerated coordinate descent through extragradient methods. And finally, we describe briefly a few other results contained in the paper and avenues for further exploration. So first, there's been a considerable recent interest in characterizing the fine-grained complexity of minimax optimization. And by fine-grained, we mean the dependence of the method on each of these blockwise smoothness bounds on the Hessian of a convex concave function f in terms of the operator norms. So several recent exciting works have made significant progress in obtaining improved fine-grained dependencies on these problem parameters. However, a gap still remains between these upper bounds and the lower bound. And in our work, we give a simple application of RL, which obtains an alternative rate for a range of smoothness parameters, improving known upper bounds in some cases. There are other ways to obtain this rate, but our framework makes the calculation very straightforward. And it would be really interesting to explore if the techniques of our paper can close the gap. We're also interested in applications of a perspective on extragradient methods known as optimism, proposed by Rockland and Sridharan. This perspective has gained interest in the machine learning community, and several works have studied its application towards training generative adversarial networks. And we show that the original optimism analysis is captured by the RL toolkit, and find exploring further applications of optimism within our framework to be quite interesting. And finally, we're also interested in developing a more general theory of variance reduction for randomized extragradient methods. And as a concrete application, it'd be really interesting to recover accelerated variance of SGD for convex optimization within our analysis framework. Thank you again for listening to our presentation. And if you are interested in some of the finer detail that were glossed over in the talk, I encourage you to check out our paper, which is linked here.